what we do today will be a rather technical lecture. So we will work on parametric resonance. The kind of the central model we consider is, as the motivation, is the pendulum with a moving support. Okay. And we consider the support moving periodically. So position of the support at time t is the same as t plus capital T, where capital T is a period. So then we can write equation of motion. So let's remember what are the equations of motion. That the second derivative of the acceleration of angular acceleration is plus gravity divided by length of the pendulum, 1 plus acceleration of the support divided by g, by g sine phi equals 0. So that's simple equation, but now we have time dependence. Time dependence of the coefficient, and this is what gives the name a parametric resonance. So the effect that we will consider are connected with periodic dependence of coefficient on a parameter or on time. The periodic dependence on time on a parameter instead of the periodic forcing that we considered last time. So the way we write this equation, we define the vector y, which has two components. So that's phase space vector in two components. And then this equation it can be written as y dot equal j yt, with the right hand side is just, so the first component is the derivative of, so let's just write this first. So there are two components in y, where the first component is velocity and another component is, first component called angle, another velocity, and then y dot can be written as j yt, where j yt is defined as, so first component psi dot equal phi dot equal psi, and double dot comes from here, so minus j over L. Yeah. And we have two properties of the field. So we know that there is equilibrium. So in our case, it's 0, 0. And the equilibrium means that it's a solution. So it means that the right-hand side should be 0 for all times. And then the second condition is the periodicity. This is what we had physically as a periodic position of the support, but now mathematically it means that the right-hand side of the equation is periodic in time. So it doesn't change if time changes by period for any y and t. So these two conditions, and that's it. So then under these conditions, we will study this equation of motion, where from now on we temporarily forget that we are about working with a pendulum, but we will consider this equation as a mathematical ordinary differential equation. So y will be some vector of n-dimensional space. Okay, so the question is how to solve. Right, so how to solve. So I already mentioned that even equation without temporal dependence is very difficult in the nonlinear case, and there is still no complete theory. So with time dependence, it's even worse. But at the same time, if we consider small oscillations, everything becomes simpler. And small oscillation is a situation where we consider much better. We know much better, so we consider small oscillations near the equilibrium. So it means that the distance between vector y and y star is small. So what we call it, I should call it x, right? So y will be equal to y star plus x. And we assume that x is small. So it's small oscillations near the equilibrium. And then we can consider linearized system as usual. So how we do is we remember that we take the right-hand side and we expand it in Taylor near y star. So we expand only in the first variable. So it gives you g at y star t plus the matrix that I will define in a second. Y minus x, right? Oh, so let's make it more. Maybe it's okay. So we write it as g of y star plus xt. And now we make a Taylor expansion in x, right? Because x is small. So when x is 0, we get the 0th term. And then the first order term will be some matrix. It depends on t by x. So this is Jacobian matrix. I will show what it is. And higher order terms. So what is G? Is a Jacobian matrix of our function with respect to the y coordinate at the equilibrium. So what it is, it's a matrix of derivatives. So we take g1 dy1, g1 dy2, g2 dy1, g2 dy2, gn dyn. So it's n by n matrix. N by n matrix of derivatives, and it's taken at exactly at the y star, but still there is a t variable. So t variables remains untouched. So that's why the Jacobian matrix, you do this at every time. So you get every time you get different Jacobian matrix. Okay, so this is expansion, and what we know is the first term is 0 because this is exactly our equilibrium condition, right? And this is small. So we can neglect it in linearization. So whenever you do consider linearized problem, system, let's say system. The system you obtain by neglecting higher order term. So what you get is y dot, which is derivative of y star plus x, right? On one hand side. And on the other hand side, it's approximately is equal to j yt, which is can be approximated by this formula. So by GTX. So on this expression, derivative of constant is 0. So you get x dot equal GTX. So we get the linearized problem, which is looking just like the linearized problem that we had for autonomous systems, but now it's non-autonomous. So now the matrix G is time dependent. And in our case, it's periodically time dependent because the original matrix small g was periodic in time, so its Jacobian matrix is also periodic in time. So this matrix is the same after each period. So we have to find this linearized problem. So this is linearized system. So we have original system and linearized system. Still, this system is complicated. And what we actually do it's complicated because it depends on time. So we don't have a very good, essentially, so the way how we solve this system, which is time dependent periodically, is through the Poincare section that I already mentioned. So that's the idea how you go from continuous time to discrete time. And in discrete time, you don't have any more, the system becomes autonomous. So let's remember what does it mean. So Poincare section. So the idea of Poincare section is that you consider your y space and time, so it's space and space time, and you consider you take the initial point at time 0, and then your solution is just certain curve, and we will consider this curve by making snapshots at the integer number of periods. So all what we're look at where was the solution at these times. And now we only look at that position. So forgetting what happens in between. So this way you define yk as y at time k time periods. So k is integer. So k, this integer number k becomes our new time. It's like you, for example, if you look, your period is 1 minute. So your new time is how many minutes, at how many minutes you look at your state. So 1 minute, 2 minutes, 3 minutes, and so on. But you never look. But you stop looking what happens in between. And the idea is that between each adjacent periods, the dynamics is the same. So if you know the map which associates initial condition to the state after a period is the same at each interval. So we can say we can call this map Poincare map. And we know that after each period, it's the same map that maps initial value at the beginning of the period to the value at the end of the period. So it's always the same map. Okay, so that means that there is a map which is mapping at every period. It's just the same map that maps initial to final points. Good. So this is a discrete system which is analog of which is reduced form of the continuous time system. So in the same way, we can introduce and connect the equation for small oscillations, so the linearized equation. So consider small oscillations. So first of all, the equilibrium condition is that after a period the point does not change, right? So this is the equilibrium condition. So that condition for the solution which which remains constant, our y star. And we can consider small oscillations near the equilibrium just in the same way. So we consider yk as y star plus xk. So xk is a difference, so we assume that xk is small. So then what you can do, you expand now in the Taylor series the right-hand side. So f at yk will be f at y star plus xk. Now we expand it in Taylor. Taylor with respect to xk. And it's the same story. So first you compute f at y star at x equals 0. And then you get Jacobian matrix that we will write down what it is by xk plus small high order correction. So now f is our Jacobian matrix of our function f. So what it is just the same story. So df1 dy, dy1, df1 dy2, f2 dy2, dfn dyn. So the matrix of all derivatives from all components, and it's computed at y equal y star. So next, what we understand, remember that this is just y star because of the equilibrium condition, and this is small. So for linearized equations, you neglect this part, and you get linearized system. So let's write it first in original form. So yk plus 1, y star plus xk plus 1. It's one side. Another side, it's equal to f yk, which is approximately what we obtained there. It's y star plus f xk. You cancel y star, and we get linearized system as xk plus 1 equal f xk. So this is our linearized system in discrete time. So discrete time picture of the motion is more limited because you don't know what happens in between. You only know what happens at every section. But at the same time, what we gain is that this system is now autonomous. So you see matrix F, which is standing there, is just constant matrix. So there is no time dependence of the matrix, while in the previous linearization, the matrix was time dependent. So moving to this discrete times, we gain this autonomy. The system becomes autonomous. So what is missing is make a connection. So we can now make connection. somehow made a connection. We make a connection between, connection. So relation between continuous and discrete time systems. So what's the connection? So the connection about the original systems, which is nonlinear system with continuous time and the nonlinear system with discrete time is rather clear. So what you, so if you solve equation of motion with some initial condition y0, then you define f of y0 just as a solution at a single period, no? Because this is exactly what is y1. So you take a system, you solve in the interval between 0 and period. So solve in the one period, and you get the value which is the value of this function f. So this is how in practice you obtain discrete time nonlinear system. And in the same time you obtain the system for the linear system. So what we do for the linearized system, for linearized system, we do it in a slightly better form. So what we do, we consider n by n matrix, which we call fundamental solution, matrix x capital of T, which we call fundamental solution. So this will be a matrix which solves just the same equations as a linear equation. So this is the same equation as a linearized equation. But now instead of vector we put a matrix, and we solve it with initial condition to be identity matrix. So we solve this Cauchy problem, initial value problem. So whenever you solve it, so what you can find is that then it means that solving this problem, you can solve the problem just for the vector. For arbitrary initial condition, so then this problem is solved by x of t equal capital F of t small x0. So you can check that this is true, because whenever you have this value, so initial condition is really x0, because initial value of x capital is identity, but x0 gives x0. And whenever you substitute this here, you will get that previous equation multiplied by x0. So it's also satisfied. So this we have. But now what you see is that f is a solution that connects. So now we know that f is a matrix which connects the value at 0 time to the values at the period. And from another side, we know that we can write it through the fundamental solution. So this gives us what is F. So we know that F is just a fundamental solution at one period. So this is a practical way how to find this F matrix. So what you do, you solve this linearized system with initial in the matrix form with the initial condition to be identity matrix. So remember, this is just 1, 1, 1 on the diagonal. You solve it, you compute it at one period, you get the matrix F. So this is what we call Floquet matrix. So there is full connection. So we can write systems in continuous time, we can write it with discrete time, and we can connect the equations in discrete time. We took equations with continuous time. So getting the autonomous system for this discrete time. Okay, so what do we have? What do we have? We started with a system with periodic coefficients. We considered equilibrium. We said that we want just to solve the system near the equilibrium. So we can linearize it, and we came out with the autonomous linearized system in discrete time. So this is our object. So we now will see how to solve. So all this path was made to compute this system, which we can solve. So this we can solve. So so next step will be to solve this system. Because solving that system, we will understand much about our original system in continuous time. So our goal now is a general solution of system, dynamical system xk plus 1 equal f xk, where k is the integer time. Good. So how to solve this system? You already see that this is a system with a matrix, and we already use that systems related to this matrix can be solved through the linear system, can be solved using eigenvalue problems. This is what we will be doing. So let's write eigenvalue problem. Fu equal, so we will call eigenvalue rho. So this is eigenvalue problem for the matrix F. Remember that eigenvalue problem means that we are in a complex space in general. So what you can see is that whenever you have eigenvector, then you can immediately find a general solution. So uk, which will be equal rho ku, is a solution of this problem. So how to see it? The proof is just substituted into the problem. So you see that f xk equal f rho ku, rho you put outside. And now remember that this is eigenvector. So it's you add 1 to the power, and this is exactly uk plus 1. So very simple proof. So having eigenvector, we have a solution. So the observation is that if rho is real, then you can choose eigenvector to be real as well. No? Then uk equal rho k u is a real solution. Now, if rho is complex, and then also u is complex, in that case, you also have eigenvalues which are complex conjugated, right? So there's a pair of the complex conjugated eigenvalues, eigenvectors. Then you can real part of rho ku and imaginary part of rho ku are solutions, are real solutions. So this you can see because this is still a solution, but it's complex solution of our system, but system is with a real coefficient, so real part gives, so real solution and imaginary part gives another real solution. So for example, so what it is, what is real part, imaginary part, we can just remember what it is. So real part of this expression, how you do, you can take out the absolute value of rho, right? And then take a real part, it will be cosine k phi real part u minus sine k phi imaginary part of u, where rho is written in polar coordinates. So then you just directly find the solution. And also you can write imaginary part. So this part you can also write in the similar form. So just very simple exercise for you to do. So essentially for each eigenvalue, real eigenvalue, we have real solution. For each pair of complex conjugated eigenvalues, we have pair of real solutions. So this already gives us a general solution in a situation when all eigenvalues are different. So let us recall where the eigenvalues come from. So let's rewrite this eigenvalue problem by putting everything to the left. And since u is not zero, so we're not interested in zero solution, then we know that determinant of this matrix should be 0, which gives us n complex roots. Roots counting multiplicities. No? So they can be multiple. So when all of them are distinct, so all of them are simple, in that case, the corresponding eigenvectors are linearly independent. So they make a basis in the linear space. And in that case, xk, which is a linear combination of these roots with eigenvalue in power k by eigenvector is a general solution. It's a general solution because it's a solution, and also what you can check is x0. When you put 0, it's just basis expansion of the initial condition. Right? It's basis expansion in basis. So in that case, we have a general solution. In general, it's a complex solution. Yeah. So its components can be complex. So you can make an observation that it can be written in real form. So in real form, using these solutions that we wrote before. So if you, instead of for the complex eigenvalues, if instead of taking this part, you take just real and imaginary part with arbitrary coefficients, you still get solution, but it will be written in real form. So you can write it in real or in complex form. So we'll see in example how to do. So that solves the problem in this particular case. So when all of the eigenvalues are simple. And then we have a general solution. We know everything about the solution. So let's take a couple of examples. Consider example. Example 1 is a function f to a matrix f to be to 1, 1, 2. That's simple matrix. So let's solve this equation, discrete time equation which is iterated by this matrix. So then, so what we do, we have to write characteristic equation, which is determinant of 2 minus rho 1, 1, 2 minus rho, which is 2 minus rho squared minus 1, which is 1 minus rho 3 minus rho. And it should be 0. So you get two solutions, rho 1 equal 1. So one root. And for this root, we can write, we can define eigenvector from the expression. So you essentially subtract 1. So it will be 1, 1, 1, 1 u, be 0. So then we also get eigenvector. u1 is 1 minus 1. And then the second root will be free. And eigenvalue problem. So minus 3, it will give you minus 1, 1, 1 minus 1. So the eigenvector is 1, 1. So at the end, we get a solution, general solution of a discrete system is sum of the two. So it will be C1 rho 1 k u1 plus C2 rho 2 k u2. Now remember that rho 1 is 1, so it's just C1 on the vector 1 minus 1 plus C2 3 power k by the vector 1, 1. So we get a general solution. So that's That's a general solution of the system, or a discrete time system. The second example take f to be 0, 1, minus 1, 0. So then we compute characteristic equation. It will be minus rho 1 minus 1 minus rho. Rho squared plus 1 equals 0. So we have two solutions, rho equal imaginary unit and another complex conjugated minus. Then we find eigenvector. So we have to subtract imaginary unit. This gives you eigenvector, which is 1i. Should be minus I. No, good. Correct? And the eigenvalue which is complex conjugated gives you eigenvector which is complex conjugated as well, so we don't need to compute it. So at the end we get two solutions. So we get two solutions which are of this form. So xk, we have to write, I didn't write it. So xk will be first arbitrary coefficient by the first solution. So what it is, it's modulus rho squared. Modulus rho squared, so modulus of rho is 1. Yeah? So we don't need to put it. And then there will be cosine. So then phi is pi over 2, right? Yeah. So what we get is that it will be cosine k pi over 2 by a real part of the eigenvector, so 1, 0, plus sine minus kp over 2 by the imaginary part of the vector, 0, 1, and plus b multiplied by the expression that I didn't write. So it will, you can check that it will be sine kp over pi over 2 by 1, 0 plus cosine k pi over 2, 0, 1. So check. So that's also general solution. So this is general solution. So how you check that it's general solution? In that case, for example, you have to satisfy arbitrary initial condition. So compute what is x0. At 0, cosine will give 1, sine will give 0. So it will be a 1, 0 plus b 0, 1 equal AB. So really by computing, A is the first component of initial condition, B is the second component, and this gives you the solution. So this example also works. So whenever we have all eigenvalues distinct, we have a solution. Now let's see what the third example, which will show that whenever the eigenvalues are not distinct, we are not done yet. So example 3. Is consider the matrix F, which is 3, 1, minus 1, 1. Characteristic equation. Three minus rho, 1 minus 1, minus rho. Determinant. This is 3 minus rho minus rho plus 1. This opens up, so it will become rho squared minus 3 minus 1 minus 4 plus 3 plus 1 plus 4 minus 2 squared. So we get that rho 1 and rho 2, they all equal 2. So multiple. Multiple eigenvalue. And let's find eigenvector. So you subtract 2, will be 1, 1 minus 1 minus 1. And you see that just we only have one eigenvector up to a constant. So you cannot find more than one, which means that we only have a solution which is uk equal any coefficient by rho k u, which is c 2 power k 1 minus 1. Of course, it's not a general solution. Of course, because you cannot satisfy arbitrary initial condition with just one coefficient. So that's the question: what to do? What to do? So the next step is just to update the whole our strategy in order to have a general solution, and the way we do is exactly the same way as we did for linear systems with continuous time. Is going to Jordan chain and Jordan normal form. I will give it in brief form after the break. So let's make a short break. Okay. So what we do if when the eigenvalue is multiple? So essentially we're interested in then when eigenvector, okay, multiple. So essentially this example, we just have multiple eigenvalue and just one eigenvector. So there is not enough eigenvector to satisfy any initial condition. So now we recall that we have a concept of generalized eigenvectors. It has to do with the Jordan chain. So we can define a Jordan chain is a sequence of vectors where the first is eigenvector. And the other, they are defined by adding the previous one to the right hand side. And then there are, in principle, k of them, some number of them. So we don't k. Let's put L. So k. I use k for other reasons. Okay. So there is a chain of vectors. So whenever you have this chain of vectors, you can check that if u1 is non-zero, then automatically all others are also non-zero. And what is important is that whenever we have a chain of vectors, so what you can check, which is good exercise, is that we have a k independent solutions. So which are the solutions? The first solution is xk is just the same as we had before, rho power k u1. So this is a solution which we already checked. The eigenvector by the eigenvalue in power k. But then you can also form solution with a second vector. So it will be rho k u2. But this is not solution because there is one more component here. So but if you add k rho k minus 1 u1, this will be solution. So check. So check that this is just solution of our system. So the solution of the system. Well, let's just do it. Let's prove. So we have to check that fxk is what we substituted here. So it will be rho k f u2 plus k rho k minus 1 f u1. Now we use the first two equations. So it will be rho k plus 1 u2 plus rho k u1. So this is by substituting the second equation. And then here we substitute the first. It will be plus k rho k u1. And then you sum this term with that. u2. And this is exactly xk plus 1. So this is a short proof. Checked. And so on. And we have until the last solution will be constructed out of the full sequence. So it will be rho k ul plus k rho k minus 1 ul minus 1 plus so on. So the general term will have the form k factorial divided by L factorial k minus L factorial rho k minus L u1. So essentially you can find the sequence of solutions. We can find a sequence of solutions. And another property is that whenever you put consider them at initial time, so initial time k equals 0, what do you have? So all of these solutions, so first is what? First is just give, what we will use is that the theorem, which is consequence of the Jordan normal form theorem, is that there exists a basis constructed using generalized eigenvectors. So you can choose generalized eigenvectors for different eigenvalues such that they together form a basis. And the corollary is that a general solution is defined using a linear combination with a linear combination of solutions of those solutions that we did here, of those solutions to star, for all vectors, for all generalized eigenvectors from this basis. So we have basis of generalized eigenvectors. Take all of them, and for all of them, take these solutions. The initial conditions are exactly the vectors of the generalized eigenvectors. So if they form basis, so you have a solution, and it satisfies arbitrary initial condition. So that gives you a general solution. So in order to see that everything works, let's just continue to finalize the example 3. So we saw here that we don't have a general solution, so now let's construct the general solution using generalized eigenvectors. So the continuation of the example 3. So we have this matrix F, which was 3, 1, minus 1, 1. We found that eigenvalue is 2 and it's multiple, double. Then we found that Fu equal U1 equal U rho U1. So the eigenvector gives you, eigenvector is what? 1 minus 1. So one eigenvector for double eigenvalue, it means that there is a generalized eigenvector. Let's compute this. Fu2 equal rho U2 plus U1. So f by so then this can be written at f minus rho I u2 equal u1. And this difference, so you subtract 2 from the diagonal, so it will be 1, 1, minus 1, minus 1, u2 equal u1, 1 minus 1. So solution is not unique, but we just need any vector. So u2 can, well, there are many which I took in it. Let's just be consistent. Which I took here was 0, 1, 1, 0, 1, 0. You can take actually 1, 0. You can take 0, 1. All works. So then that means that the general solution is constructed as the first one with arbitrary coefficient. So linear combination of the first one. Let's just write rho ku1 plus arbitrary coefficient by the second one. So what it is C1 to k 1 minus 1 plus C2 to k 1, 0 plus k to k minus 1, 1 minus 1. So that's a general solution. And just if you want to make sure that it's general, so compute initial conditions. So initial condition will give you C1, 1 minus 1 plus C2, 1, 0. Everything is 0. And it will be C1 plus C2 minus C1. So you see, by choosing C1 and C2 properly, you can satisfy any initial state. So that's a general solution. So in the case of multiple eigenvalues, you may need to use generalized eigenvectors, and then you get a general solution. You see that it's very, very similar to what we had in the previous case. So now the next step is a stability theory, which we should also describe in a similar way as we did before, but there are some differences. So let's remember what we did. So we have the original system, so the continuous time. Time system and discrete time system. In the continuous time system, we had y dot equal j yt, where j was periodic. In discrete time, it was simpler. Xk plus 1 plus f xk. Then, no, y. X, y. Then we had the linearized system. The linearization gave us, on the left-hand side, it was x dot equal g of tx. On the left-hand side, it was in the discrete version, it was xk plus 1 equal f xk. So there is this duality. So now we can define stability. the Lyapunov stability. So how you define Lyapunov stability? For this system, it's just the same definition as we had. So it tells you that the solution, the equilibrium is stable if, so we can, this is actually general solution, general statement. So the equilibrium y star is stable if, so in the continuous case, it's if for any epsilon positive, there is delta positive such that whenever you take initial condition delta close to the fixed point, you continue to be epsilon close for all times. And you can formulate just the same condition for the discrete time, but now in discrete time version. So for any epsilon positive, there is delta positive such that whenever your initial condition is delta close, it remains epsilon close for all, for k big equal 0. So essentially the same story. The same story, but here its time is continuous, here time is discrete. And also we can say that y star is asymptotically stable if additionally, which means that we just keep all what we have, but additionally the limit of the solution as time goes to infinity is y star. So it at large time it ends at y star, and here it's just the same thing, but in discrete time. K goes to infinity is y star. So there is a direct analogy of the stability properties of discrete time system and continuous time system. So graphically, if you're on the y on the phase space, so it tells you that whenever you, if you don't want, whatever epsilon neighborhood of point y star you have, you can always start at delta neighborhood. Not very symmetric. So if you start inside delta neighborhood, you never exit from epsilon neighborhood. And in the continuous time, it means that it never exits. In time, in discrete time, it just jumps for discrete k. It also never exited discrete time. So just very similar concepts. And the important thing that these concepts, one of the concepts implies the other. So we can write theorem that you can try to prove yourself. Essentially, what we prove is that the condition on the left is equivalent condition on the right. So it doesn't matter in which discrete or continuous time you check the stability, it will be the same. So y star is stable or asymptotically stable in both cases. So is asymptotically is just stable, or it is asymptotically stable in continuous time formulation if and only if it is asymptotically stable in discrete time formulation. Well, you can try to prove, or you can look at the theory of differential equations. So this is equivalent formulation. Of course, so this is a theory of ordinary differential equations. Of course, in this theory, there are some extra conditions. Essentially, you need some regularity condition for the function g for this to happen. But in principle, if function g is smooth, this is true. So this helps a lot. It tells us that whenever we want to consider small oscillations from continuous time, we can go to the discrete time formulation, and stability is what ensures that this linearized description remains correct for large times, right? So that so the stability criterion is important for justifying why that we can linearize the system, and this linearization works for a long time. And it's hard to determine stability in a continuous time formulation, but and it's easier to do it in discrete time because we don't have time explicitly. So it's autonomous system. At the same time, the conditions are equivalent. So we just need to solve the problem of stability for discrete time formulation because these two formulations are equivalent. So now the next theorem, I'm not giving the proof. So the next theorem by Floquet tells you that solution, the trivial solution, which is just 0 for all k of the linearized system, is, and now there are three conditions. So it's stable. So let's do like this, asymptotically stable. If and only if all eigenvalues has absolute value smaller than 1. This is simplest condition. So just stable if and only if absolute values are smaller than 1. So why you need it? It's rather clear because you have this type of solutions, rho power k. You see, so why you see it? So because the solution has a form of the rho power ku, and if you compute norm, it's absolute value of eigenvalue by norm of u. So you see the norm is increasing in time k if absolute value is bigger than 1, and this will be decaying if absolute value is smaller than 1. So this is a justification of this condition. For that reason, rho is often called multiplier. So every time you go in discrete time, you multiply the solution by the eigenvalue, so by the multiplier. So this, the second condition, so it's stable if all of them are smaller or equal than 1. So the solution either decays or it remains the same by absolute value. But then there is a question about Jordan chain, because in Jordan chain there are some solutions which, if there are generalized eigenvector, there will be some solutions which will increase as a power law in K, this K coefficient. So the theorem of Loquet, it tells you that if module is smaller or equal than 1 for all eigenvalues, and eigenvalues with modulus equal to 1 are semi-simple. So no generalized eigenvectors. Because generalized eigenvectors in this situation will give increasing solutions. And the third is unstable in the remaining case. So if and only if there exists solution, there exists eigenvalue with absolute value bigger than 1, or there exists, or can be, and no, on. Or there exists eigenvalue with eigenvalue with absolute value equal 1, which is not semi-simple. So there is a generalized eigenvector. So this solution, so you can see that this theorem is almost a copy of the theorem that we had for linear systems. But the only difference is that condition for the real part of eigenvalues now is substituted by condition for the absolute value of the eigenvalue. But the rest is essentially the same, and all the reasoning is essentially the same. So if you compare, you will see a very close way how you prove this theorem as well. And then there is a direct connection. The second theorem by Lyapunov is also direct extension of the theorem that we had before. Which relates stability of linearized system to stability of the original system. So we know that whenever we obtain linearized system, we neglected some terms. So it is not automatic that stability of linearized systems gives you stability of the full nonlinear system. And here, these properties are equivalent to the properties for the discrete time version. So we need to know when stability of this system or instability of this system implies stability or instability of the full nonlinear system. And the theorem by Lyapunov is just analogous to what we had before. So it also gives just two cases. So if absolute value of all multipliers is smaller than 1, so its absolute value is smaller than 1 for all multipliers to all eigenvalues of matrix F, then the equilibrium of nonlinear system in that case it's whatever one, so the discrete or continuous time, it's the same thing for stability, is asymptotically stable. And the second is that if the the absolute value is bigger than 1 for at least 1 for some, which means at least 1 eigenvalue, then Y star is unstable for a nonlinear system. So again, the same limitation. So we only have then. So it's so this is sufficient condition, not necessary, and we only have two cases. So we don't cover all the situations possible. So there is a Lyapunov special case when the theorem doesn't work. So this is when all eigenvalues have absolute value smaller or equal to 1, and there are eigenvalues, or there is at least one an eigenvalue with absolute value equal to 1. So this is just the same special case as we had before, but for real part of eigenvalue. So now it's for absolute value. So the same situation. So the linearized system is working for all times in the first case, and we know that it never works for all times for the second case. So we have a very strong criterion. So just knowing eigenvalues of the system, we know what happens in the original equation near the equilibrium. And there is, and you see that it's not always that linear system describes what happens in the nonlinear system, because the difference is this Lyapunov special case. So when we're not in the Lyapunov special case, these properties are the same. When we're in a special case, they can be different. So linearized system can be stable, nonlinear unstable, or vice versa. Linearized system can be unstable, but nonlinear can become stable. So you should be careful. Special case is always a big problem. I'll just go to draw the picture. So the linearized system. So linearized system, we have a real part of rho, imaginary part of rho. We have a unit circle. And for the asymptotic stability, we need to be inside. So if all eigenvalues are inside unit circle, we have asymptotic stability. The stability, which is not asymptotic, so when the eigenvalues are not necessarily go to when the solution is not necessarily goes to the equilibrium, is when you everything inside but some of them are exactly on the unit circle, but semi-simple. So in that case, we have stability. So that's Floquet's theorem for the linearized system. And finally, whenever one eigenvalue is outside the unit circle, we have other can be in, it's okay. But it's enough to have at least one of them to have instability. So this is three cases which correspond to stability, instability, asymptotic stability of the linear system. And for the nonlinear system, situation is slightly different. So for nonlinear system, the first case is just the same. So if all eigenvalues are in the unit circle, then we have asymptotic stability. We have instability. Here instability are in two cases: when there is eigenvalue on the imaginary axis, or eigenvalue which is not semi-simple on a unit circle. So not semi-simple. So there are Jordan chains. There is a Jordan chain which is associated to this eigenvalue. So for the nonlinear system, it's different. So what we can guarantee is that whenever there is eigenvalue outside the unit circle, we have instability. And all the rest falls into the intermediate case is when everything is inside the unit circle. Everything inside the unit circle, but there are some eigenvalues on the imaginary on the unit circle. So this gives you special case. So in that, so there is difference. So for linearized system, we know everything. So there is asymptotic stability of everything inside, stability everything inside or on the unit circle, but only unit circle should not create generalized eigenvectors. Instability is when at least one of them outside or on a unit circle with a generalized eigenvector. And for nonlinear system, we know less. So there is these two cases where at the left and the right where we guarantee what happens. So there's asymptotic stability if all eigenvalues are inside. There's instability if one of them outside. And whenever all of them are inside on a unit circle, it's special case. So in that case, we don't, just by eigenvalues, we don't know what happens. Just by solving linearized system, we don't know exactly what happens in nonlinear case because it can be either stable or unstable. So it really depends on nonlinear terms. So there is this difference, and it's always important to remember that there is a difference. So when you solve a linearized system, it does not. There are situations where you don't guarantee that the same conclusion is true for the nonlinear system. Okay. So that's it for the general theory, and now let's go back to the pendulum, and we have to solve it. So we have to solve it during today and the next lecture because we don't have much time left. And we still have to study waves. So pendulum. So first we will consider consider again our pendulum with a moving support, which is periodic in time, going up and down. mass, angle, gravity. So what we will do, we will take a special case. So the most natural special case of how you put it, move the support up and down is a cosine. But cosine we will consider only in the case when h is cosine. We don't have an explicit solution. So we will take first the h exactly in the form where we can solve the equations. This helps very much for seeing what happens. So we consider h in such a form. So we'll start, remember that what we have in the equation of motion is acceleration. So h double dot, not h. So first we'll write what is h double dot. So we take h double dot in such a form. So it's, well, that in notes the plot is horrible. It's not even correct. But anyway, we do it like this. So we take a constant value until a period, until half a period. Then another negative constant value until period, then constant value until free half of the period, then 2 periods, and so on. Okay, so just the support accelerates up, accelerates down, accelerates up, accelerates down. So from this picture, what you can see is that if you can find h, which is just integration. Once integrating it once, you get h dot. Integrate twice, you get h. And so what you can check is that what you will have is that you will have this picture. So this t to t. You will have parabola here, another parabola here, parabola here, another parabola here. It looks like cosine, but it's not cosine. Every section is a parabola, 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 parabola. So I can write what it is exactly. So what we will take h of t to be delta divided by 2 omega t minus pi. Remember, we can always connect t to the frequency. So we take this when 0 is from t to t over half, and delta over 2 omega t minus pi 2 pi minus omega t. So just check that it's correct. So this is a formula of h, which is parabola and parabola. And then continue periodically. And then h double dot will just give you, when you differentiate it twice, you'll have omega squared by t. This time you will have omega squared. 2 will cancel, so it will be omega squared delta. And minus omega squared delta here. So this value will be omega squared delta minus omega squared delta. And this value will become delta pi squared over 8. And this value will be minus delta pi squared over 8. So delta is essentially amplitude of oscillations, and omega squared delta is amplitude of acceleration. So that's a system that we want to study now analytically. And I will write and we will write equations of motion, and then we continue next time. Okay, so what we do, so first remember equation of motion. The equation of motion it is phi double dot plus g over L 1 plus h double dot over g sin phi equals 0. So what we do, we define different times. So instead of time t, we will consider now a time tau, which is omega t. Remember that omega is related to period. So when you do this, and then second derivative will be what? So will be the second derivative of time by 1 over omega squared. Right? So then equation becomes d phi d tau squared plus so they will so essentially, in order to obtain this from that, we divide both sides, this side by omega squared. So it will be g over L omega squared. And then we simplify it further. D squared over d tau squared plus, we call it A plus B h of tau equals 0. And what is what? So A is this coefficient. Right? B we take construct from that. So B, well, we take B is actually delta over L. Delta over L. And remember, H double dot is omega squared delta. So omega squared will cancel. G cancels. So what will only remain is delta over L. So that means that H of tau is just 1 or minus 1. And also, we change it from t to tau. We change the period from t capital to 1. So what happens here is that this happens from 0 to pi, and this happens from pi to 2 pi. So the function h is the function of tau now has period of 2 pi, and it's just 1, minus 1, 1, minus 1, 1, minus 1. So this is kind of a changed coordinate equation which describe the pendulum. And if this function h is nice, so it's just 1 minus 1, 1 minus 1 with a period 2 pi. And then in the same way as we did with the usual pendulum, we can make a linearized system. So we can linearize system near the equilibrium. Which is phi 0. So near this equilibrium, it means that small angles. So it means that angles, velocities, also double velocity, etc., are all small. And if they're all small, what we can do with the equation, we can expand the sign in the Taylor series and approximate it by the linear term. So we get the linearized system. In this equation. So we have nonlinear system. And we have linearized. So now we have nonlinear linearized. Now we know that by studying linearized system and using this knowledge, we can try to make a conclusion about nonlinear system, about its stability. And this we will do next class. So the only thing I put is that this equation is called Meissner equation. So we have to, the advantage of this equation is that because h is piecewise constant, we can solve it. Because whenever h is constant, we know the solution. And it's just different constants in different intervals. So we can solve this equation, find the Floquet matrix, find its eigenvalues, and using these pictures, we can say whether the equilibrium will be stable or not. So whether the vertical position when the vertical position will be stable or not, and we will know conditions under which it become unstable, and this is exactly conditions of that video that you considered. So when you had a swing and you have to stand up and sit and stand up in order to succeed to swing the pendulum, and this is certainly should be done in the under the instability conditions. So this instability condition is what we want to determine, and we do it next time. So there's still much work, but hopefully we succeeded in the next lecture. Okay, so thank you. Tomorrow, Monday.